What if engineering worked consistently and completely independent of any tools, from process engineering planning to full integration in a control system? Is this just wishful thinking, or is it already possible today? Today, we will be presenting this concept and the technology behind it in a brief video. We will start with an evaluation of the situation from the viewpoint of a user, Dr. Otten. In your opinion, what is the status of the tools and interfaces necessary to make this dream a reality? Thank you very much for the question, Mr. Block. Before I answer it, I would like to take a look at the bigger picture. The requirements in the process industry, in particular in the specialized chemical and pharmaceutical industry, are better flexibility in production and faster time to market for products. The COVID crisis has recently demonstrated this. The means used to achieve this are modularization and digitalization. In addition to the physical module, the encapsulation of the automation technology is required for modularization. This is achieved via the MTP. The MTP is practically the operation model, the digital twin of the module. With it, we have a standardized description of the automation technology of the module, which is relatively easy to integrate into the orchestration level. Therefore, the MTP is not only relevant for process modules, but also for package units. However, with the standardized description of automation technology in the form of MTP, there is also, and now I will come back to your question, the possibility of partially automated engineering of the MTP or automation technology. This is based on process planning or system planning, also known as RMI. We can carry out data-supported integrated engineering in a much more simple and error-free manner in the MTP than we can through classic engineering and automation technology. Because of this, I'm very excited about how far we have come with integrated engineering of MTP today. Mr. Otten, thank you very much for your assessment. We are addressing exactly the challenges you described with consistent engineering, from process engineering to automation, by using MTP, the module type package. In a joint proof of concept with our partners XVisual, Semodia, Phoenix Contact, and ABB, we will demonstrate how we can use partially automated generation of the operation model to reduce manual work, avoid errors at transfer points, and shorten the time to market at the same time. The starting point is process engineering, which is handled in Plant Engineer from XVisual. The resulting P&ID serves as the basis for filling an MTP as much as possible from a process engineering standpoint. This MTP already includes a description of the operator display and important individual control functions. In this context, the MTP is exported via MTP Engine from Semodia, which is integrated directly into the P&ID engineering tool Plant Engineer as a software library. The exported MTP is then imported into the MTP Designer tool from Phoenix Contact as part of module engineering. This provides the basic structures for implementing the automation engineering behavior, which are then fleshed out and specified further. The services are also implemented during this step. The MTP can be re-exported and transferred to the operator from the time at which the structural expansion is completed. This means the operator can already start integrating the MTP, while implementation of the behavior on the control level is completed in parallel. Integration is then completed in process orchestration from ABB, which allows direct controlling of the services and individual control levels. However, the best way to understand all of this is a real-life example, a dosing. Let's start with P&ID engineering. Thank you very much for your introduction, Henry. Here we see the P&ID for our dosing module. The module has a container, an inlet and outlet with valves, a pump, and relevant sensors to measure various process values. Since the P&ID of a module is prepared in process engineering anyway, it's a good idea to use the P&ID information to create an MTP in order to reduce the workload. Now, I would like to present the process for adjusting the P&ID and MTP export in Plan Engineer in more detail. Plan Engineer is a P&ID software based on Microsoft Visio, with a user interface that integrates seamlessly into the Visio interface. Here, we see the user interface of the software shown with our P&ID module. However, the P&ID is not just a simple graphic drawing, but rather a representation of a complex informational model that describes the P&ID in the background, and which is supplemented by data that can be used to generate the MTP, for instance. In this module, there is still no sensor for measuring the temperature of the container, so I will now add one and specify it for the export. To do so, I will open the library icon in Plan Engineer and look for the icon I need to display the measurement. I will simply place it on the flow diagram via drag and drop. Then I will select an intelligent connector tool, which I can use to insert a process connection line between the sensor and container. Next, Plan Engineer opens the Properties window. Here, I can now define the function number of the sensor and specify what kind of a measurement this is. In addition, I can specify whether the sensor should be shown in my MTP here. First, I use a relevant characteristic to define that the sensor should be displayed visually in the operating screen of my MTP as a visual object. In addition, I assign an E-class number for the sensor, which gives a standardized description of the type of sensor to be displayed. Furthermore, I can use the relevant characteristics to create communication attributes for the sensor so that the measured value can be read out in the POL environment. In the case of the sensor, I define an ANAView attribute, short for analog view of the temperature. In addition, I define the scaling range, which is between 0 and 120 degrees in this example. This means that for each icon on the P&ID, I can define whether the icon should appear on the MTP operator display, and to what extent it should be able to be measured and controlled by the MTP. The limits of my operator display are defined by the dashed module frame. I can easily initiate the export of the MTP via the user interface. To do so, I assign it a name, click Save, and the MTP is exported after just a few seconds. The body MTP created this way can now be imported into an environment for the engineering module. Thank you very much, Niklas. Here we have the MTP Designer, a software tool from Phoenix Contact that is used not only to create and edit MTP files, but also to automatically generate SPS project bodies. Now I will show you how you can implement the module programming simply and cost-effectively. First, the file generated by XVisual is imported into MTP Designer. The file is supplemented with information specific to Phoenix Contact. To do so, we can now define or adjust the interfaces, which were not yet known at the start of system planning. For example, we can now define a communication interface for the motor. In addition, we can define services and create additional procedures with just a few clicks. I will create a dosing service, for instance. An additional procedure is added to this service. Now, the expanded MTP file can be exported. The file is sent to the system engineer and read in by POL. This ensures fast commissioning of the system, since a sequence can already be created while I and the PEA engineer continue to process the SPS program. First, I will export a project body that contains all necessary interfaces. Next, I will switch to PLC Next Engineer. This is a software tool from Phoenix Contact that is used to create the SPS projects. So far, I have integrated the libraries here and set the IP address for the SPS. Now, I will import the generated project body. Here, we can see that the appropriate function blocks are created in the SPS program. The project is already compiled free from errors and can therefore be uploaded to an SPS. However, for an example, I will connect the newly created measurement point TI005 with dynamic data. To do so, I will transfer the seconds from the system time to this measuring point as a value. Then, the project can be uploaded to an SPS. Ralph, please show us how simple it is to integrate the module into the system by using the MTP file. Thank you very much for sending the MTP file. Now I can insert it seamlessly into the process automation. To do so, I will first start the ABB Orchestration Designer. I can insert the PEAs here and plan the production process. I could also prepare this work step offline, which is done especially for standardized PEAs. In the next step, I need to configure my communication. Then I will apply the configuration to the process orchestration level, POL, and thereby load the graphic images and the recipe. After the offline configuration is completed, I can run the integration test with Oleg. One key technology used in MTP is the service-based interface. A PEA does not have to be addressed via individual function blocks. Instead, it allows the assembly to control via services. The process orchestration level starts and stops services, and the PEA implements the commands autonomously in module automation. We can use the ABB's service controls to operate the services. As we do so, we will observe the visualization of the function blocks. Once the operation is working, the PEA can be integrated into the recipe of the orchestration level. As you can see, consistent engineering is already easy to implement with the tools and technologies available today. Please contact us if you have any questions.